At this point, we'll now try and understand the effect of adding a derivative action to our controller. So adding derivative action to the P controller we were just looking at. Here again is our closed loop transfer function. So in this case, C of S will have a different form. In general, the addition of a derivative control allows us to anticipate the error. So if we're looking at how our error is changing with time, with proportional control, the control effort was proportional to the error. So in order to make the application of control larger, we needed the error to be larger. But with derivative control, we look at the slope, or the derivative. So even if the error is still relatively small, but it's sort of ramping up, that means that the applied control will also increase even before the error gets large. And so this is quite a useful fact, and it in essence allows the system to have improved damping, because if the error is starting to take off, the control effort can work to combat it sort of early on. Something that we've discussed previously is the fact that differentiation can amplify noise. So we discussed this when we talked about signal processing and we were doing numerical differentiation of a noisy signal. And so this fact means that we should never use D control by itself. We should always use it in conjunction with proportional control, or proportional control and integral control. This fact also makes some people in industry hesitant to use derivative control in their controllers. Later in the course, we'll discuss some methodologies for addressing this amplification of noise problem. So here's our controller. It has a constant that's proportional to the error, and then multiplication by S causes differentiation of the error, and another constant to make the control proportional to the derivative of the error. If we substitute it in to our closed loop controller and rearrange, this is the closed loop transfer function that we get. So looking at this, it's not a canonical second order system because of this 0. That being said, we can still use this transfer function to sort of build some insight. So we may not be able to predict the precise behavior of the system, but we can at least understand the trends in terms of the effect of increase in KD. Specifically, we can see that Kp, the proportional control, again affects omega n, just like it did when we had P control all by itself. And here we can see that Kd affects the sigma term, or the zeta omega n term. So if omega n is held constant, increase in Kd increases zeta. And this is sort of what we had just discussed, but it increases damping. Another way to sort of build intuition for this is if you think back to our discussion of dampers and dashpots, you may recall that the force generated by a dashpot is proportional to the velocity or relative velocities of the two ends of the dashpot. This is a similar case where the control is proportional to the derivative, just like velocity. If we went a step further and looked at the steady state behavior of this system, i.e. applied the final value theorem, took the limit as s approaches 0, this term would go away, this term would go away, this term would go away. So the effect of all the KDs would go away, and essentially we'd get the same behavior we got when we had just a proportional controller by itself. So the addition of the derivative action did not help our steady state error. Okay. One nice thing about this type of controller is that it's 2 degrees of freedom, just like the PI controller we showed earlier with that earlier example. That is, we have a second order system with 2 poles, and we can place those 2 poles anywhere we'd like by tuning the Kp gain and the Kd gain. For example, one way that people often tune PD controllers is they first use KP to increase the speed of the system and reduce the steady state error through its effect on omega n, and then they use KD to bring down the overshoot through its effect on zeta. Now we will discuss the effect of adding integral control to our controller. So here again is our closed loop transfer function. With integral control, the control effort gets larger as the error is accumulated. So you can sort of imagine that the integral term is integrating the error. And so the longer the error goes for, the more the integral builds up, because an integrator is a summer. It calculates the area under the curve. So here's the form of a PI controller. We've got the term that's proportional to the error, just a constant. We divide by S to perform the integration and multiply by another constant. If we substitute that into our closed loop transfer function and rearrange, we get something of this form. Looking at this, it's definitely not canonical. Not only does it have a zero, but it's also third order. So it's a little more challenging to draw general conclusions about the effect of integral control. But it often tends to make the system slower and more oscillatory. And so one reason that is maybe you can imagine, is in order for the effect of the integrator to take hold, you need to sort of sum up the effect of the error. So if we can sort of imagine our error doing something like this, in order for the effect to build up, we need to add up the area under the curve. But if the error switches sign, then the sort of direction that the controller is pushing doesn't necessarily change sign. So we've built up this positive area. This will still be positive even when the error changes sign. And so what we have to do is we sort of have to unwind the integrator. We have to subtract all of this error off, subtract what's been built up in the integrator before we can start to push in the other direction. And so this can tend to make the system slower to react and can also tend to make it more oscillatory. Looking at the effect of integral action on steady state performance, we can again apply the final value theorem. So we take the limit as s approaches 0 of s times y of s, where y of s is the output of our closed loop system. This quantity here is the transfer function, y of s over r of s. We have a unit step reference, so this is our r of s. Taken together, we have our y of s. So the s from the input cancels the s from the theorem. We then can see again that we have a denominator where all of the coefficients are positive. Therefore, we will again have a system where the poles have negative real part. We can then solve this limit by simply substituting s equals 0, since the function is defined for s equals 0. So that goes away, that goes away, that goes away, that goes away, and we're left with b times ki divided by b times ki, which equals 1. And so what that means is, for a unit step reference, for a command of 1, the steady state value of our closed loop system will always approach 1. That means the steady state error is 0 for a step reference, which is a very useful thing. This tends to be the biggest benefit of using integral control, as it helps the steady state error. It's interesting to note that even if we use a very small ki, even if we don't use very much integral action, the steady state error will still go to 0. The thing is, it will just take a long time to get there. So the longer we integrate for, the bigger the control effort builds up, and eventually it builds up enough to to offset the error. But if Ki is quite small, that process may take a long time. To summarize, we've learned some intuition about the effect of the three terms of a PID controller by looking at a canonical second-order system. Specifically, we saw that increasing Kp corresponds to making the control effort larger for the same amount of error. It tends to make the system faster, tends to reduce steady-state error, but it can also make the system overshoot more. Increasing the derivative action allows the controller to anticipate an increase in error, thereby sort of damping the system. A drawback is that it can amplify noise. The addition of integral action tends to help reduce steady-state error, but the fact that we have to wait for the integral to build up, and then when the error changes sign we have to wait for the integral to unwind, makes the response slower, possibly. A caveat is that these guidelines do not hold for all situations. So this is sort of the intuition that we built for a canonical second-order system. A lot of this intuition will hold for other systems, but it doesn't necessarily hold if we have a system that's not a canonical second-order system, if it's higher order, if it has zeros. So specifically, we need to actually dig into the mathematics, look at how the poles move around, look at how the zeros move around to actually understand the true effect of the control gains. For systems that are not canonical, we may need to use trial and error. And one approach is to try and look for a reduced order approximation. Try and identify if there are any poles that dominate the response. Try and identify if any of the zeros cancel with any of the poles. And so if we can take a higher order system and approximate it as a first or second order system, we can use some of this intuition. And this table here sort of summarizes what we were saying on the previous slide, but again, it's not always true. Okay, so if you recall, increasing Kp tends to help steady-state error, tends to make the system faster, but it tends to cause more overshoot. The addition of derivative control didn't help the steady-state error, but it tends to add damping and make the system settle quicker and have less overshoot. Integral control, the addition of integral control tends to help steady-state error, but it may make the system slower or more oscillatory. So this brings us to the conclusion of Module 14. In this module, we introduced an approach to controller design. First, we discussed how to specify the requirements for a control system. In particular, we typically use parameters related to the step response of a system as its specification, its settle time, its rise time, its overshoot, etc. We also introduced a pole placement approach to control. So the idea is that we interpret requirements in terms of pole location or transfer function parameters. So we have some specification in terms of speed, whether that be peak time or settle time, or we have some requirement on overshoot. And so we take those requirements and we translate them into pole locations, or more generally parameters related to pole location, like sigma, like omega d, etc. We then find the closed loop transfer function so that we can see how the gains affect the transfer function, how the gains affect the closed loop poles. And we solve for the gains to match the desired poles parameters. If this is a canonical system, then we're done, because we have exact relationships between the parameters and the time response. If it's not a canonical system, we can often use these relationships to sort of guide our tuning, but we will in general need to iterate in order to get the exact performance we desire. We then introduced PID control, which is one of the most prevalent controller structures found in industry. And we tried to build some intuition for the effect of the P term, which is the term that's proportional to the error, the D term, which is proportional to the derivative of the error, and the I term, which is proportional to the integral of the error.